as you might guess from the way that we came up with the number, there is a relationship between the number e and compound interest. And it's this. If we compound interest often enough, we might as well just suppose we're always compounding it. So whatever little bit of time you can think of, the interest is compounded over that little bit of time. And it turns out, because of the relationship that that number e has with the compounding formula, that we have a strange looking but actually related formula that gives interest compounded continuously. What are the quantities we're interested in? We're still interested in the starting amount. And we're still interested in R, the interest rate, as a decimal. But now, of course, we have no interest in N, because N is just as big as we'd like. For interest compounded continuously, we have the form, the principal at time t is equal to the starting principal times e to the R times t. Now, there's something I want you to notice in comparing this to interest compounded with some frequency. And the specific thing that I want you to notice is, here we add 1, here we don't. Here, R appears in the base, here, R appears in the exponent. These formulas really look unrelated, and in order to get to their relationship, we need calculus, which we haven't got yet. But these two totally different looking formulas, it turns out, give very closely related information. For most numbers, if I plugged into this formula with n equals 365, or plugged into this formula, I would get the same result when I round to the nearest penny. Okay, how do we use this formula? Suppose George puts $1,000 into a savings account which pays 2% interest compounded continuously. How much does he have after 10 years? Now, the thing that tells us we need to use this formula and not this formula is that the problem says compounded continuously. If it said compounded monthly, for example, this is the formula that we would need. Since we're going to use this formula, we're going to be interested in the starting amount, the interest rate as a decimal, the final amount, and the time. This $1,000 is what he put in, so it's the starting amount. The interest rate is 2%. As a decimal, that's 0.02. How much does he have after 10 years? So the time is 10 years, and the final amount is what we're looking for. So plugging into our formula, we get P of t, the thing we're looking for, is 1,000 times e to the r times t. And now we can just put this into the calculator. 1,000 times e to the 0.02 times 10. And we get, rounding to the nearest penny, $1,221.40. George has $1,021.40 after 10 years. Let me give you one of these to try. Eric invests $800 in a fund that pays 7% interest, compounded continuously. He wants to take his money out when he has $2,000. How long must he wait? Round your answer to 2 decimal places. Pause the video and try this now. Okay, again we have this phrase compounded continuously that tells us we want to use the compounded continuously formula. We're interested in the starting amount, the interest rate as a decimal, the final amount, and the time. So he invests $800 in a fund that pays 7% interest. He wants to take his money out when he has $2,000. So he wants the final balance to be $2,000. And we want to know the time. So plugging into the formula, 2,000 is the starting amount times that number e to the r times our unknown time. Oh, so we have an exponential expression here that we need to solve for. So we want to get the exponential by itself. Divide both sides by 800. 2,000 divided by 800 is 2.5. And now we want to rewrite this in terms of logs. The base stays the same. 2.5 is the result of the exponential, so it's the argument of the log. And then the exponent is 0.07t, so that's the result of the log. Oh, but wait, that log base e, that's special. That's called the natural log. Okay. So I have 0.07t is the natural log of 2.5. I'm just going to divide both sides by 0.07, and I'll get t is the natural log of 2.5 divided by 0.07. No need to screw around on the calculator. I definitely have a natural log button. Natural log of 2.5 divided by 0.07. To 2 decimal places, that's 13.09 years. Eric has to wait 13.09 years.